Hida Kamioka in Gifu Prefecture is surrounded by one of the few mountainous areas of unspoilt nature still left in Japan. And deep in a mine in Hida Kamioka, Super Kamio Kande has been built. On the basis of the results obtained from experiments with the previously constructed Kamio Kande, the size has been increased tenfold, so that the amount of water the new tank holds is 50,000 tons, much more than the 4,500 tons in the previous tank. The changes mean that the number of protons that are available for observing detectable events has been boosted to 25 times the previous number. The photomultiplier tubes, light sensors, have been increased in number to 11,200 units. Their sensitivity doubled and their installed density improved by 100%. Because Super Kamio Kande is 1,000 meters below ground, massive earth pressure presents a problem. It is as great as 2,700 tons per square meter. Fortunately, the strata here are classified as the oldest in Japan, and the bedrock is therefore firm enough to support a large excavated space, 40 meters in diameter and 58 meters in height. Construction of Super Kamio Kande began in December 1991. The first step was the excavation of a large pit. In order to complete this within the short space of 2.5 years, advanced mining techniques were employed. As each section of the excavation was completed, it was sprayed with concrete. Long anchoring rods called rock bolts were inserted at 1 meter intervals, and concrete was again sprayed. In this way, sufficient strength was ensured to fully withstand the tremendous pressure exerted by the earth. This research facility is 1,000 meters below ground. If it were built above ground, experiments would be hampered by the large number of particles that would clutter observations. But most particles cannot penetrate far into the earth. So if we take ourselves deep below ground, they cannot follow us. In one of the side tunnels is a facility for water purification. The smallest amount of impurities or bacteria in the water will lower its transmissivity, and radioactive elements will cause background signals. This facility produces water purified to the highest possible degree, and by constantly circulating it, maintains the purity at all times. This is the computer center. It lies about 3 kilometers from Super Kamiokande. Data from observations are processed here, and new methods of processing the data are being developed. But even if new methods are devised, data comes in at the rate of 10 full items every second, and buried in the data flow are items of real importance. So that none of these will be missed, the speed at which they are gathered and the speed at which they are processed are extremely important. How to store as a precaution all of the huge amount of data collected minute by minute and how to retrieve necessary data rapidly are among the crucial questions that are subjected to repeated discussions and examination. A large number of light sensors are installed in the tank. When charged particles move at high speed through water, a faint bluish-white light is produced. This is known as Cherenkov radiation. When a proton is destroyed or when a neutrino is caught, particles are created. Light is produced in the form of this Cherenkov radiation. This light is caught by the light sensors. These sensors are called photomultiplier tubes. When they receive light, they produce electrical signals called photoelectrons and amplify them. The photomultipliers here are 50 centimeters in diameter, making them the largest in the world. They have also been developed into the most sensitive. These large photomultiplier tubes are made by blowing, as you see here. Skilled craftsmen blow the glass into large, thin-walled tubes. This is delicate work, beyond the capabilities of a machine. The glass tubes are then sent to a factory, where technicians carefully turn them one by one into finished photomultiplier tubes. Technicians fit completed electrodes in place in the glass tubes. They are given special training for just this task. The glass edges then have to be joined together in a process called sealing. Because the seals must be able to withstand considerable water pressure, this process is a very important one. After the glass has been sealed, a polarizing plate is used to check for distortions. Any distortions that are found in the glass are removed by a careful process of annealing and slow cooling. A photoelectric surface, which will produce electrons by absorbing light, is formed by depositing the element antimony on the inner surface of the glass. Cable connections must be able to withstand water pressure equivalent to 4 atmospheres. They are therefore waterproofed by treating them with a special resin. Over a period of 4 years, 11,200 photomultipliers were manufactured in this way. In July 1994, the gigantic underground space was completed, and work immediately began on constructing the water tank. A number of methods had been devised to save as much time as possible on the construction. One of these was to give the tank a 20-sided polygonal cross-section in order to make the difficult process of bending stainless steel unnecessary. Despite the great size of the underground space, it was not sufficient to allow the use of a tower crane or scaffolding of the usual type. An overhead travelling crane was therefore installed on the ceiling and used to set the sheets of stainless steel in place. Sliding scaffolding was employed and raised in keeping with the pace of the construction work. It not only filled the role of scaffolding, but also had to be able to withstand the pressures imposed by the work of placing the concrete. In order to advance the beginning of experimentation by even the shortest amount of time, the covering section of the tank was assembled on the floor of the excavated space. At about the same time, performance tests were being run in the computer center on the ATM module, which was to be used for Super Kamiokande. About 10 weeks was required to complete the 934 check sheets. A unit called an electronics hut, in which the electronic circuits, high voltage power source, and the data collection and processing equipment would all be housed, was brought in through the narrow tunnels. The electronics hut was lowered to a point 40 meters below the ceiling unit by crane. When installation of the electronics hut was complete, interior work began. Photomultiplier tubes were installed on the ceiling. Then came the climax of the construction work on the tank, raising the 270-ton ceiling unit by crane. With jacks fixed in the upper section of the side walls, the electronics hut was set on top of their horizontal plates, and with photomultipliers hanging from its undersurface, it was raised about 5 meters a day, taking about 1 week to be hoisted into position. The huge tank was now complete, 39.3 meters in diameter and 41.4 meters high. These are photomultiplier tubes that were carried deep into the mine. The research staff personally put them through a performance check one by one. Following this, the photomultipliers were prepared in one of the side tunnels for final installation. In order to begin experiments as soon as possible, a timetable was drawn up to set 7,650 photomultipliers in position on the sides of the tank within a period of about 2 months. This meant installing an average of 204 tubes a day. So that this could be done, it was decided to arrange the tubes in sets of 3, called units. 4 units could be arranged in rows to form one module. And by installing the photomultipliers in module form, it would be possible to shorten the time needed to put them all in place. Triple tube units were therefore assembled in 4 rows to form 12 tube modules. This work was dangerous, because if a tube broke, it could cause a serious injury. Even so, the members of the research staff set to work carefully and quickly, and completed the whole task themselves. The space surrounded by the arrayed modules is called the inner detector, and it is this space that is being used for the experiments. The space outside the structured array of modules is called the outer detector. And behind the modules, small photomultipliers have been installed. These have the role of detecting cosmic rays penetrating deep below ground. The work on the outer detector was done under the supervision of researchers from overseas. A large number of researchers from other countries are taking part in the project. A hoist was used for rapid installation of those modules on the side walls. When each was hoisted, another was attached to it from below, and this was repeated until 17 modules formed a column reaching to the top of the tank. Positioning of the photomultipliers has a great effect on the results of monitoring. They must be positioned with a tolerance of plus or minus a few centimeters. Positions were checked and adjusted repeatedly. When photomultipliers were in position, cabling was installed. Work gondolas were suspended in the outer detector between the photomultiplier arrays and the tank walls and used to lift cables bound together in threes. To avoid their becoming tangled and the danger of wrong connections, each cable was labeled with a destination address and the work went forward carefully. To undertake this part of the work, researchers had to obtain licenses to operate the gondolas. The cables that had been lifted into position were run into the 4 peripheral electronics huts set at the top of the tank. Each photomultiplier had a 70-meter cable attached to its back. 11,200 cables were gathered together from their various heights. The high-voltage power source and the ATM module circuits, which digitize the analog signals that are received from the photomultipliers, are housed in the peripheral electronics huts. These signals are taken into an online host computer located in the central electronics hut, and signals emanating from the same events are brought together. These signals are then sent by fiber optic link to the computer center outside the mine. The final modules are now being hoisted into position. The space remaining for this last column is very tight. A close watch is kept as the column is lifted carefully into place. The inner walls are now covered with shining spheres. One would be justified in speaking of a glass tank. On November 11th, an early ceremony was held to mark completion of construction, even though only half of the photomultipliers were in place on the floor of the tank. The long-awaited moment arrives. Ultra-pure water begins to flow into the tank. Two months later, the tank is full. The facility is almost complete. Researchers use a boat to install the final photomultipliers around the perimeter of the lid. The tank is closed. The darkness inside awaits the advent of faint lights. After about 4 years, research can now begin with the completed Super Kamiokande. The whole scientific world is now waiting to see what results this facility will produce.